Welcome to Electrochemistry Screencast number 2. Standard cell potential, or the electrochemical potential E0, is one of the quantitative ways that we can measure the tendency of reactants to form products, providing things are in their standard states. Now, what are some other quantitative measures that we've seen for this? Well, one is delta G, or free energy change, and another is K, or equilibrium constant. And one of the things that we might be interested in is how these are related to each other. And it turns out that E and G, or E0 and G0, are related to each other by delta G is equal to negative NF E0, where N is the number of moles of electrons transferred, F is the Faraday constant, which has a value of 9.6485 times 10 to the 4th coulombs per mole. And then E, of course, is the cell potential, or the reaction potential that we've seen many times before. By the way, here's a picture of Michael Faraday as a young man. Here's Michael Faraday a little bit older. And here is a picture of Faraday's workshop. And this is Michael Faraday giving a public lecture in 1856, which was very popular at that time with some of the new discoveries in electricity and magnetism that he partially was responsible for and also popularized a bit. Anyhow, away from history now, a little bit of an analogy. So here is an excellent analogy involving dams. And what we often do as a way of sort of visualizing electric current and electric potential is to think of things in terms of, instead of electrons flowing, of water flowing. And the potential is something like the height of a dam. So it's like the potential energy, which is higher as the dam is higher. Water is stored at a higher height, so it has more stored energy or more potential energy. So if we have a tall dam, it's a large electric potential by analogy, and if we had a low dam, wasn't as tall, it would have a lower electric potential. And then the flow of water over the dam is analogous to the flow of electrons through an electrochemical cell or in a reaction, and the amount of electrons that flow is a product of the number of moles of electrons and the Faraday constant, which is the charge of 1 mole of electrons. So there's higher and lower potential. The electrons flow from high to low potential. And if we have more electrons flowing, then we have a larger current. So that's an analogy we often use. And now back to some equation stuff. Remember that at equilibrium, we've seen a relationship between delta G0 and K. Delta G0 is equal to negative RT log K, natural log of K. We've seen this in the thermochemistry chapter fairly recently. And then remember that we now have found that delta G0 is equal to negative NFE0. So we have two things that delta G is equal to, one in terms of the equilibrium constant, K, and one in terms of the reaction electrical potential, E0. And so what that means is we can equate the two. Negative NF E0 equals negative RT natural log of K. And if we divide both sides by negative NF, then some things cancel. And that leaves us with E0 is equal to RT over NF times the natural log of K. So there is one relationship where if we know the equilibrium constant K, we can take its natural log, multiply by R and multiply by T, divide by number of moles N, and divide by the Faraday constant F, and that will give us E0. And then, of course, we could solve this equation for K in terms of E0, and we'll leave that to you to do if you'd like to try. And it turns out that K, the equilibrium constant, is equal to E to the NFE0 over RT. So all of this is in the exponent, and notice the distinction between E0, the cell potential or the reaction potential, and small e, the number that is the base for the natural logarithm. So here's an example involving a calculation of this sort. This is a reaction we saw in class. Lead ion reacts with aluminum to make lead and the aluminum ion, and the potential, standard potential E0 for this is 1.53 volts. So first of all, just a review question. What does E0 mean to be plus 1.53 volts? What does this value for this reaction mean? And of course, since E0 is positive, that means the reaction is spontaneous, or we could say product favored. And 1.53 volts is a fairly decent sized electrical potential, so the reaction is quite spontaneous or quite product favored. Now let's use our new knowledge to calculate the delta G0 value for this reaction and think about what that means. And note, we know the E0 value. We now have an equation that relates E0 to delta G0. So delta G0 is equal to negative NFE0. And N, you might be able to see from looking at this reaction how many moles of electrons are transferred. But lead gains 2 electrons. Each lead ion gains 2 electrons to make a lead atom. But then there are 3 lead ions involved in the reaction. So 3 times 2 gives us 6 moles of electrons. And if we look at aluminum, same idea. Aluminum loses 3 electrons, but then there's a coefficient of 2 here, so 2 times 3 gives us 6. So we have 6 moles of electrons transferred. The Faraday constant is 9.6485 times 10 to the 4th coulombs per mole, and the cell potential, standard potential, is 1.53 volts. So we multiply all those together. Don't forget there's a negative sign out in front. And moles cancel, and note that a coulomb times a volt is a joule, so we get negative 886,000 joules, which is negative 886 kilojoules, which means the reaction is spontaneous or product favored, and this is a pretty darn big delta G0, so this is quite spontaneous, quite product favored. Okay, so fairly straightforward calculation, but a little bit, you have to be a little bit careful to make sure you get the number of moles of electrons right, and then also pay attention to units, that coulombs times volts are the same as joules. One way also, just quickly, to look at this in more detail, if you have trouble looking at the reaction equation and picking up just from the overall equation the number of moles of electrons, you can always do the half reactions. So there's the lead half reaction and the aluminum half reaction. And then to get the moles of electrons gained and electrons lost equal, you would triple the reduction half reaction for the lead. And then we double the aluminum half reaction, the oxidation half reaction. And now note, the number of moles of electrons gained are 6. Number of moles of electrons lost are 6. That's what we use for our number of moles. And of course, if we added things up, that would then cancel out. So in a sense, the number of moles of electrons gained and lost has now become hidden once we get the overall reaction. But if we take it apart, we can figure out what that would be. Okay, back to this question now. Same reaction, but now let's calculate K for this reaction and see what that value means. And we have an equation, new equation now to calculate K. It's E to the NFE0 over RT. And these are all values now that we've seen before. So 6 moles for N. Faraday constant, same as before. 1.53 volts for the E0. R is 8.3145 joules per Kelvin, and the assumption here is we're working at 25 degrees Celsius since nobody said anything differently. And now note, moles cancel, Kelvin cancel, Coulomb times volt is a joule, and then joules cancel, and all of our units cancel, so our exponent is just going to be a number, and e to the all of this multiplied and divided appropriately, all of that mess, gives us about 2 times 10 to the 155th. And again, some of you might have calculators where the value, your calculator won't even calculate it, it goes to overflow. So it's a huge number, so very spontaneous, very product favored reaction. And then, how good is the agreement between these values, E naught, delta G naught, and K, and what each means? So here's the summary. E naught, 1.53 volts, positive. Delta G, negative 800, delta G naught, negative 886 kilojoules. And K, 2 times 10 to the 155th. And notice all of those say very spontaneous, very product favored. We've seen delta G values before for comparison, and we know this is a very big negative number. We know this is a very big K, and now we're starting to get some familiarity with the size of E electrical potential, E naught. And in this case, 1.53 volts may not seem like it's a very big potential, but look at what it compares to in terms of equilibrium constant and delta G naught, and so that gives you a little bit of a feeling for the scale of things. And that's it for Electrochemistry Screencast number 2.